Well, first of all, thank you, Fredo, for inviting me here, and thank you all for at least turning up for the last talk. So my talk's made of two bits. The very first is the queer matter, which is of course my introduction as to being a gay man in science. And I think if you'd asked me this 10 months ago when I lived up in Nottingham, my response to that would have been quite a bit different. Effectively, it would have been a non-response. It was a non-issue. I didn't really speak about it that much. Maybe my colleagues might disagree, but things changed quite a bit when I moved down to Brighton, mainly because the community was very different to Nottingham. I went from being a very introvert gay to a very extrovert gay, to say the least. One particular anecdote I remember having with my professor much later, a few months into my PhD here, when he was asking how do we get new PhD students to make friends in Brighton. How have you made so many friends, Reece? You can't really tell your PhD supervisor that was through gay Facebook. However, generally my experience has been very, very positive. My work colleagues have happily embraced the extrovert Reece. They've very bravely come out on big gay nights out with me. Some of them even attended my musical birthday, which of course, if you look at Brighton, was of course in Bar Broadway. Some of you may remember it. But other than that, I mean, I can only speak from my own personal experience, and all I've received is not only positive experiences, but also embracing and a very open culture from colleagues from Nottingham, but also my new colleagues down here in Brighton. And so, to end that spiel, I'll then move on to the second part of my talk, from queer matter to the ultra-cold matter, which is my field. And before I jump into that, I kind of have to define really one of these words, in particular, what I mean by cold. And this is actually quite a big problem when you're a physicist. Oops, jumping ahead. Cold is very difficult to define when you're dealing with very small particles. Of course, when you're a human, you can just stick a thermometer in your ass or under your arm. But a bit too gay there. And that, of course, then tells you the temperature. However, when you're dealing with very small particles, you can't really do that. Thermometers are far too big, and atoms are far too small to pin down. So in physics, temperature, as an equivalent principle, is also defined through velocity. Velocity, oh, there we go. Just mix around because I don't use maths. So temperature and velocity are actually equivalent principles when we talk about physics because of a thing called statistical mechanics. And so we consider the temperature of the air in this room, for example, which should be about room temperature, but probably a bit more now. That's about 20 degrees Celsius or 300 Kelvin in physics terms. And actually air, we can equivalently talk about moving at a velocity of 1,600 kilometers an hour, which is incredibly fast. And when we consider the very deep regions of outer space, the image left over from the Big Bang is actually very cold. That's almost near zero, minus 200 degrees Celsius, minus 270 degrees Celsius, or almost 3 Kelvin. And that's still quite fast for perhaps the average atom, which is about 180 kilometers per hour. So when I talk about ultra-cold atoms, which is what we do, our research deals with, we're talking about things that are even much, much colder. These are atoms that are moving at 100 nanokelvin, which I won't even bother defining in Celsius, because it's so near zero, it's effectively negligible. And atoms moving at that temperature are moving at a snail's pace. So 1 centimeter per second, which is ridiculously slow for atoms. And the reason this is important is the definition between what is normal and what is quantum, which is the whole point of our research, is all defined, all becomes interesting when things get really that cold. And so many of you might be aware of the idea that light can be acting both as a particle and as waves, but that's the same for matter. But matter only does that, or at least only does it in certain circumstances, and the interesting circumstances when it's really, really cold, so that's the region of about 100 nanokelvin. And this is really interesting for us because then they start to behave as quantum items, and start to experience quantum properties. And these quantum properties are really particularly useful for us because we can then use them to measure certain things which weren't really possible when these atoms are much hotter and so acting like particles. And this is pretty much the topic of our whole research, which is where I think I might have to jump back a few slides. Which is what do we actually do with ultra-cold atoms? And this is kind of give you a bit of motivation for my whole talk. And so that motivation really comes from 4 different problems I want to kind of produce to you guys. The first is the GPS system. The GPS system is a massive headache for most of the world's governments and also a lot of defence. The GPS system is incredibly vulnerable, not only to accidental damage such as space debris, but it's very easy to disrupt if you're intentionally trying to disrupt it, such as with an EM jammer. And so a system which is independent of GPS would be a holy grail to defence and civil contractors and general economic. GPS is so important for finance. On top of that, so this is quite a futuristic photo we just pulled from stock images, but the idea of transparent materials, also smart tech, also things like graphene. These are things that are really futuristic, but research into them requires a tool which can actually analyse these very small molecular surfaces and actually tell researchers how these things actually look. The third one kind of maybe doesn't need much justification, which is called medical imaging. Sensors which are less invasive but even more sensitive are of course going to be much more important for medical diagnosis but also medical research. And lastly, if you're talking from a purist kind of point of view, is of course fundamental research. This is of course fundamental research which is very broad in scope, but could be just very basic, kind of how do we compare our mathematical models to actual physical systems, but also very interesting things as to how can we use things that we can have in our lab to simulate things which you can't have in the lab, such as black holes. So jumping ahead a bit. So again, why does our research make use of these things, and why do we need to be so cold, and how can we solve these problems? Well, this all comes down to, again, sorry, this is the Mac problem, how do atoms behave when they get really, really cold? And so this is a GIF I pulled from Wikipedia, which shouldn't have the text removed, so I'm asking everybody to ignore the text. So what we're seeing here is actually a bunch of atoms that are slowly being cooled through a process I won't get into just yet. And what we're seeing slowly is that these atoms are much less acting like perhaps ping pong balls, and much more so they're acting like waves. And that's important because as they act like waves, like ripples in a pond, they start to interact with each other. And what is really important in this case is that when many of these atoms are together and they get cold enough, they start to act not just as many different individual waves, but start to act at a very critical temperature as one big quantum wave. And this is important for a number of different reasons. One, because you have so many atoms acting as a big quantum wave, it becomes very, very sensitive to particular properties of the universe, such as magnetic field or gravity. And if you want to do something interesting, such as our research here in Sussex, the early kind of properties that manufacturers, defence, even governments are very interested in actually measuring, and this actually being able to precisely measure these things is a huge holy grail in our research. So it's going to give you the spiel about our research in Sussex. This whole slide actually summarises it quite well. And what we're actually seeing here is devices that are just designed to trap atoms and cool them in a way, well, trap them in a way which then become useful somehow for us to do particular experiments. And so what I'm going to try and do next is perhaps use the motivation from the very beginning of the presentation and show how a number of different of these devices actually solve some of the problems I spoke about earlier. And so the first is, so this atom chip, this device here on the top right is from one of my sister labs, originally up in Nottingham and now down here in Sussex. And their whole shtick is to design a structure like this, which is actually very similar to modern computer PCBs, so that's printed circuit boards. And all they want to do is be able to trap atoms on this structure and then cool these atoms down to that big quantum wave we saw earlier. And because these atoms are so sensitive to magnetic and gravitational fields, but in this particular case magnetic fields, they want to then put these atoms above novel surfaces. So these surfaces might be things that could potentially work out eventually to be transparent novel materials, but also things like graphene. And this whole design was actually designed by some of the colleagues here, well, worked on by some of the colleagues here tonight. And it's actually already, hopefully, almost producing results, but it's going quite well. I can see a guy putting his hands in his head, almost producing results. And that's just to solve this whole thing, to create a toolbox for manufacturers and researchers to use to be able to not only push their own research, but then say, how can we make these things actually manufacturable? Then moving on to the more fundamental side of things. So this is a structure we call an atom chip. Atom chips are the kind of next generation of the kind of process from, if you compare it to the way electronics went, you had very large transistors to very kind of portable transistors now are small pocket devices. atom chips are kind of halfway along that path in terms of atomic physics. And their whole purpose, just like the PCB in the previous slide, is just to trap atoms on their surface. But they're quite important because they're so precisely manufactured that they can create really interesting geometries for these atoms to be trapped in. And that's really useful because then you can say, well, what if I just trap my atoms in a line? And then you can say, well, how do atoms behave in that really simple system, and how do they compare to the mathematics we have? Which sounds quite mundane, but it's actually a really difficult problem to pin down, because then you can say, are the mathematicians right and the rocket not, which is quite nice for physicists. But then you have to say, well, why are they wrong? And then come up with new models, and then those models kind of push the boundaries of physics and mathematics. And again, if you're really clever, you can then create even more interesting geometries to simulate systems which you cannot at all bring in the laboratory, such as a black hole, but also many other systems, such as fluid dynamics. Systems that are very hard to pin down, but because their physics is so similar to the way these quantum atoms behave, you can say, well, I can simulate it here in my experiment, and then perhaps come up with new models which will help me push theoretical physics. The third one is medical imaging, and thankfully my colleague who works on this isn't here, otherwise he'd moan at me, because medical imaging doesn't actually use ultracold atoms at all, but it's a very similar technology and uses a lot of the kind of same supplementary technology. And as I perhaps said earlier, this whole shtick of this is just to make sensors that are much, much smaller, which in principle can be held much, much smaller, closer to the head or other parts of the body, such as the spine or along nerve paths. And these sensors are so much better than perhaps are meant to be designed, to be perhaps the next generation of MRI machines, because one, they can be much lower power, but two, because they can be closer to the head or wherever you're trying to measure, they can be a bit more sensitive, and they are sensitive in themselves, and I hope that not only can they, that they will be able to map much deeper into the brain or other parts of the body. And I know the two biologists in the room already from the talk, I don't want to answer any questions on that, I know nothing about it. And lastly is my research in physics. And my research is kind of broadly related to the idea of GPS, free navigation systems, but it's actually much broadly related to the whole progress of my field, which is the idea of making structures that are much more portable, much lower power, so we can get rid of ridiculous experiments which look like this, which are actually very nice photos. But actually get rid of all these kind of optics and all these lasers, all this very expensive equipment, and make something that's much more handheld, not only for things like satellites, but also for much more handheld devices such as metal detectors, so that civil engineers can perhaps find pipes or wires buried very deep underground, or even just to have much more GPS-free navigation for your mobile devices or vehicles. And the reason I mentioned perhaps military a few times is because when they have submarines lose their GPS as soon as they go underwater, and so they can have a system which allows them to keep that kind of navigation system when they do go underwater, they'll be obviously very, very happy. So on this top right image is actually one of the steps we're trying to take in order to introduce this kind of portability into our research, which is to use very different manufacturing techniques that I introduced earlier, which is very strange atom chips or PCBs. What we looked at was using actually additive manufacturing, which you guys might know as 3D printing, to print metallic structures, which are handheld, and this is actually our first prototype, to trap atoms in a much more efficient way. Because this structure could not only much smaller, but because it's much smaller, it meant it was much lower power than what was actually available on the market, or at least what was mostly used in our sister experiments. And I saw a picture from one of our sister labs, which sadly isn't mine, but to kind of show what these kind of trapped atoms would look like. So what we're seeing here is actually billions of rubidium atoms, which is an alkaline atom, levitating in a vacuum chamber, being held by, in this case, actually, almost kind of see at the top, these like circular cores on the top and the bottom. And our whole structure was just designed to replace these horrendously big and high-powered foils, so it could sit inside this chamber and trap all these atoms. And I've probably waffled enough, and it's getting quite late. So on that note, I'll say, well, thank you all for listening, and any questions, and feel free to check us out on Instagram or Twitter or Facebook, and everyone the rest of them, you can blame me for any terrible posts.